My name is Alek Kolcz, and so this is a workshop, so it's going to be a little bit of a work in progress presentation. Hope it's interesting. So I guess whether or not you call it massive data sets or big data, I think many of you come across the problem that in some cases it's actually pretty hard to build models over big data for a variety of reasons. The reasons are multiple, but one of the not trivial ones is that, allowing to quote me CJ Lane's presentation, is that many frameworks that we use for doing stuff over big data, such as Hadoop, MapReduce, and stuff, are not really meant to, or were not really designed with the machine learning in mind. So for a variety of reasons, they're not really all that compatible with many things we want to do over them. And let's just look at a list of typical challenges that we may face. So one of the challenges deals with just the algorithmics of machine learning. Some of the algorithms, such as boosting, are just sequential in nature, so they're not that easy to parallelize. And some of the other ones are iterative in nature. So again, there is some serialization component which we have to be aware of. The second is just the way data is distributed on a large cluster. And other speakers talked to that point, is that the distribution of data over a large cluster is not necessarily random. The data could be clustered by region, by some ID space, by something else, so that if we look at a chunk of data partition, we're not necessarily looking at the uniformly random sample of the overall distribution. And depends on what we're doing with this data, this can lead to some problems, such as looking at all instances being of the same class and trying to learn a supervised model. So this can cause issues. Iterative nature of algorithms, that is an issue by itself, and especially when you do stuff over Hadoop or MapReduce frameworks, where things want to be written to disk over iterations, and this causes all kinds of slowdowns. Then there's need for communication and synchronization, which again can cause various congestions and delays on the cluster. And last but not least, there's the reliability. So what happens if some of the nodes in the computation go down or are slow or non-responsive, and can we really recover from that? So there's a lot of problems like that we have to deal with when building large-scale models over big data. So the question is, what do we do? How can we make it better? How can we make some of those problems go away? And one natural answer is, well, let's try building better frameworks, better systems over which we're doing machine learning. And this is a very valid direction to go to. And a lot of people here are interested in Spark and similar frameworks where essentially we want to make machine learning easy from the outset. And this is great, but I would say this is great but not done yet. If you look in the industry, by and large, those frameworks are still in a kind of nascent stage. They've not penetrated deep enough to be available where we want them to be available. So you may be stuck with something which is not top-notch machine learning ready yet. So another direction is actually to ask the question, do we need all this big data? I mean, do we really? And in some cases, like, we don't really need all this data. And people have pointed out that the learning curves for some of the problems are actually quite steep. And we may not need billions of examples. We may do quite well with millions of examples, or tens of millions of examples. So we don't need to go to all that scale. And this is also very valid. So to a large number of problems, we can do very, very well just by looking at stuff which fits on a single box. And by the way, the boxes that we call commodity boxes today tend to be very large, and they can hold hundreds of gigabytes of memory. So essentially, this is not the box of 10 years ago. Sorry about that. But also there is another direction. I'm going to quote the position papers from Jimmy Lin from a few years ago, essentially making the point that, okay, um, instead of going against the flow of some of those frameworks, such as MapReduce, let's maybe look at the opposite direction. Instead of trying to port every single thing we want to do into any particular framework, can we look at the constraints the framework provides and say, ask ourselves, can we find methods or algorithms which are actually compatible with this framework and exploit the fact to the limit? So we don't need to do everything, but we can maybe find a subset of things which work very well with this particular framework, and we can get a pretty long runway using them for a lot of problems. So this is what inspires this presentation. So assuming we really have this big data problem where data doesn't fit on a disk, we don't want to really downsample it and fit in a single box. We're used to all of this data. I would say typically we face two kinds of problems we want to solve in a very broad sense. So one type of typical task is that we want to take all of this data and build something reliably, quickly, easily, and without doing too much engineering, without doing too much tweaking, without spending too much time. Essentially, we want to get something that works. And this is really, I would say, the majority of cases that people face. We just want to do an experiment, have it run, take the model, look at the results. Now, there's also the other side of problems where we actually want to take all of this data and maximize a very specific thing. And usually this comes into play where we understand the problem very well, such as in ad prediction, revenue optimization applications. We actually want to solve something we understand pretty well. We probably understand a lot of the features pretty well. And we know that by looking at more of the data, we can maybe move the results a little bit, but this little bit translates potentially to a lot of money. So it makes sense to invest into a lot of engineering, a lot of tweaking, maybe special purpose solutions, because in the end there is a big payoff. But I'm not going to talk about those problems today. So then the question is, well, given that I want to build something quick and easy and reliably, don't we already have a lot of things which work like that? It's not a kind of a solved problem. I would say it's like semi-solved. So indeed, we have things which work like that. And Jimmy in his paper essentially was talking about two classes of algorithms we can apply to supervised learning problems which are kind of reliably implementable in MapReduce frameworks. So one is essentially streaming support gradient descent using logistic regression. So that works like a dream for a lot of problems. As long as we randomize the data appropriately and we take a long enough amount of time to stream everything for a single node, we can learn a pretty good model with just one pass through the data. That's fine, but for truly big data sets, it can be a nuisance too, because it takes a long time to stream all this data with lots of features for a single node. So the other direction is to parallelize it somewhat and do what I call a split and merge, a split and average, where we partition the data in some way over multiple reducers and either stream the data in a single reducer or build some other model such as decision tree, maybe iterate even over the data, and merge the resulting models in the end in terms of merging the parameters, averaging the parameters, or do some kind of voting aggregation. So it's a pretty common pattern that people use all the time. So just to put a picture on it, let's say we're doing some kind of a MapReduce programming with a pig. We load the data into our mappers. We extract the features. After we know the features and the labels, we just pump them through a single reducer. We learn the model. We store the model on the disk with some kind of a storage function or UDF, and we're done. So the model is built. And very similarly, if we're doing the partitioning style computation, we again load the data, extract features, partition, pump them through reducers, aggregate in the end, store to disk, And if we want to run those models, it's pretty straightforward, just loading to a single UDF function, applying to data, and streaming a parallel way, and we're done. So this is great. However, there's still problems with the split and merge. So it's not as easy as one might think. So what could go wrong? Well, one thing which can go wrong is, again, this randomness assumption or violation of this assumption when loading data, working with data on a big cluster. So data is not random, especially when we're dealing with supervised models. We may be loading something which is very biased in some way in one of those partitions, and the model that we're learning may not end up being very good at all. So again, the aberration is things being of a single class, and the model is likely to be useless. The other problem is just the resources. If we're doing something complex, like iterating over data in one partition, we may easily take too long or take too much RAM. So the thing is going to blow up, and we're going to be kind of stuck in debugging this thing just to tweak the parameters so the thing works. So the bottom line is, we're doing things in that way, we may have to be quite careful how we structure a computation and think about it pretty hard. So it's doable, but not always quick and easy. So it'd be nice to have something even simpler than that. So I would say probably the simplest thing of all we can do is just count. And this is something that MapReduce does very well. And the question is, what can we accomplish with just counting? I would say one obvious model that we can do is just naive Bayes, right? That's just counting. So in a supervised setting, we just take class labels and feature instantiations, we pair them up, we count them, we can do it very well and reliably in MapReduce in a distributed fashion. It doesn't really depend on how we partition the data doing so. At the end of the day, we just get the accounts, we sum them up, and the model is ready. We can apply the model to new data. So this is great. However, as we all know, this is not necessarily the best model. So the model has many potential problems, especially when features tend to be correlated. But it provides a little bit of an inspiration of the direction we'd like to go to. We'd like to get something like the simplicity of naive Bayes, and it's kind of fit with MapReduce framework, but doing maybe a little bit in a more sophisticated way, do something better, do something more interesting. So can we find more things like that, which possibly counteract some of the simplifications of this particular model? So this is what I want to investigate here. And to kind of give a context for this, let's kind of go back to this basic split and merge. So as I mentioned, once we split data, we can do a variety of things in a single partition. And one thing we can do essentially is do SGD streaming. Another, which is pretty common, is to learn a decision tree, kind of like random forest style of variety of random forest. Now, when you're learning the tree, we're iterating through the data, and we're choosing how to split the data over a single feature or some kind of a transformation of features, and we do it over and over again till the tree is deep enough or dense enough or performs well enough, and we move to the next tree. However, what if the structure of the tree is given to us up front? Then we don't really need to iterate for anything. We just essentially put each data item through the tree, look where it lands in terms of which leaf contains the item, and just update the counts per that leaf. So at the end of the day, we merge the results of this over all partitions. We get the model corresponding to this tree. Well, where is the structure of the tree coming from, since we have not learned it? So one possibility is to get a random tree. So although we might think that random trees should be useless, they're not necessarily useless, because in a large ensemble of such trees, although the accuracy of any particular tree is going to be not very good, we have the benefit of diversity. So the trees are going to be very diverse. when we aggregate them together, we have the benefit of reducing the variance component of the generalization error. So this is great, but it also kind of rings a bell. So when we start thinking about predetermining some random structure over our input representation, that actually opens a door into a lot of experiments people did early on in pattern recognition, especially in the area of vision. So when the whole research in the 50s and 60s took off, people really started looking at neuroscience, the cortex models, the brain models, the retina models, and one particularly elegant model people looked at was just the model of gross simplification of vision, where we have the input projecting some kind of like binary retina, which bits corresponding to individual features in our problem. And instead of doing stuff over those very basic features, people looked at essentially grabbing subsets of those features at random from this retina and calling them more complex features. So the intuition is if we cover the retina with those kind of subsets of individual features, every individual basic feature is covered at least once. But in the end, we have some kind of a nonlinear randomized representation of the data, which should be useful in classification. And to some extent, it mimics to how things are connected to the real retina in biological systems. So this was quite interesting then because people were looking at various hardware implementations and, by the way, looking at such small n-tuples of things connected to bits looks very much as an address to physical memory, so we can kind of build those things in custom hardware implementations, even FPGAs. So let's take a look at how it works. I'm going to call it Bledson-Browning n-tuple because those are the two guys who came up with this architecture in the 60s. And in this case, we have an innate feature space over binary features, and we're looking at one particular instantiation of an input. The features are ID'd essentially through 1 through 8 in this case. And what we're doing, we're essentially taking one feature, second feature, and third feature. Imagine this is done at random, and we call it essentially a single n-tuple taken out of this original representation. The n-tuple is defined by the indices in this case that we sample, and it's got a particular value. And you can see if those values, the values are binary, if you can see is the n-tuples are small, this is very much like some kind of like a address in memory we can think of. So how is it different from a random tree? And I would say this is a special case of a random tree. If we start taking random trees over some subsets of attributes, they're going to look somewhat like the left side in this picture. So some of them are going to be fairly flat, some of them are going to be fairly deep, and there's going to be a great variety of them. Taking the regular n-tuples, like in this case, is going to create balanced, kind of almost perfect trees, where each possible path from the root to the leaf is going to be instantiated, and essentially with an n-tuple we have like 2n leaves, and we can hang this tree from any of the features in the n-tuple, and it's going to pretty much look the same thing. So that's the difference. So in terms of mapping this onto the MapReduce framework, is very, very straightforward. We take the root node in our job, we do this n-tuple partitioning, we distribute it to all of the nodes taking part of the computation, so that everybody knows the mapping of all possible n-tuples or trees, if you like. And then, depending on how we partition the data, we just pump all the instances through all of the individual partitions, and each partition is going to try to essentially count the number of occurrences of each n tuple in the data. At the end of the day, we just combine and merge those n tuples, a count, if you like, and we have our model. So the interpretation of those n tuples can be probabilistic or binary. So what I mean by that, we can count the occurrences of each potential n tuple in data, or we can just do a flag. Did it happen in our data or not happen? And one might think that this binary is going to be useless, but not necessarily so. If we have large orders of those n tuples, even for very large data sets, we're going to see that a lot of the values are not going to be present at all. So even just by this simple masking, we can learn the useful model, although we have more power by just doing the counting and looking at the frequencies. In terms of the aggregating of those counts, we really have two options. We can look at this as an ensemble of trees, and for each potential n tuple value, we can look at the, for example, looking at the posterior distribution of class labels in our problem, and do the simple mean aggregation, weighted mean aggregation, like we do in ensembles of decision trees. However, we can also look at what inspired this computation, which is naive Bayes. We can think of n tuples being only loosely correlated or even not correlated with one another just because of the randomness of connectivity. And our model in the end can consist of just class conditional probabilities over those n tuples combined via the Bayes theorem in a very similar way to what we do with naive Bayes. So, and one can think of doing some tweaks over those two, but those are the two basic ones I'm going to think of. But there is also the question of the binary feature representation, the binary feature assumption. Clearly, not everything that we're dealing with is binary. So most of the time, we're going to have a mix of attributes. Some of them are truly going to be binary. Many of them are going to be categorical. Some of them are going to be real valued. So what do we do then? The obvious thing is to discretize. So to the extent our features are already integers, that's pretty simple. We can just take the integer and look at the possible bits. Don't have to do anything. We can use something called a thermometer code, which is proportional encoding of integers, or we can discretize the data using a supervised method such as an MDL, or even percentile-based discretization, which is, again, very fast. So in terms of maintaining the simplicity, doing percentile discretization of data on Hadoop essentially is a push-button process. So let me give you a flavor of how well this can work. It's not a very extensive evaluation, but just to provide a flavor. So in this case, I'm going to look at a comparison of how this works vis-a-vis logistic regression, which is kind of the workhorse of all of classification we do, and naive Bayes, which is the baseline. So I'm going to look at a couple of data sets, which are real data sets, corresponding to multi-class problems. Just for the example, I'm going to look at two one versus all problems taken out of those two data sets. Data sets are tiny, really, but this is just to provide an illustration of the performance. So we're talking about 1 million to 5 million training examples. We have pretty severe class imbalance, though, and about 3K to 7K binary features. So I looked at the number of n-tuple configurations. We have two moving parts, the number of the order of an n-tuple n and their number. And to pick the number, we can think of how many times each of the individual features should be part of any of the n-tuples. So there's some kind of like oversampling, if you like. In this case, I looked at the oversampling rate of 10, which was constant for both experiments. And the evaluation here is pretty simple, just looking at the area under the ROC curve. So the results are, well, the smaller problem A. Strangely enough, naive Bayes in the vanilla flavor outperform logistic regression for this particular problem. But we managed to outperform naive Bayes in this case for two settings of the n over the ones we looked at. In problem B, it was more usual. Naive Bayes was worse than logistic regression, but we still were able to beat naive Bayes by quite a big margin for this one. So those are essentially two toy problems. What we can face when we apply that scale, especially over text data, is the sparsity. So since we don't care about what we take n tuples of, we can essentially take n tuples containing very frequent features and very infrequent features, in which case if two frequent features were correlated at the outset, they're likely going to be correlated in the end too. So there could be a variety of more intelligent sampling strategies if we know something about the distribution of the features up front, which again is fairly easy to compute. MapReduce is just counting. So just to conclude, this is just investigation in progress, work in progress over something which potentially could be quite useful because it's very simple, very reliable, easy to do in MapReduce, something to add to a toolbox. Many more experiments should be done just to confirm that it's indeed something useful. And in particular, want to do more comparisons with random decision trees and see if there's benefits vis-a-vis the n-tuple architecture. But hopefully this was interesting, and I'm going to finish with that.